Great. So thank you for the introduction. I'm the business developer at Technolution, or one of the business developers, I must say. My interest is in the high-tech industry and big science. Just a quick introduction in Technolution. Very quick, but we are a company in the Netherlands with around 250 people. We have a lot of expertise in electronics development, embedded software development, programmable logic development. We offer research and development to our customers, services to our customers like supply chain management, lifecycle management. If you would like to know more than just ask me, I will just show a couple of examples of what we do for our customers and where our interests are for the digital industry, but also for space technologies. So Technolution, we are a Dutch company. But we are actually active all over the world. So we have 3 offices in the Netherlands. We have activities in Denmark, in Sweden, in the UK, and also in the United States of America. But okay, let's now focus on what we do for the high-tech industry sector. And that's what we do with our brand Technolution Advance. Where with Technolution Advance, we actually develop solutions for the advanced high-tech and big science systems, such as data acquisition and data processing systems, or image processing systems and image analysis systems. And there, of course, we apply our electronics development, our embedded software development, programmable logic development, and a good portion of systems engineering to come up with great solutions for complex problems. Just a couple of examples are, for instance, a high-speed data processing for a metrology system, where we help as a technical developer Near-field instruments. Near-field is an incubator from TNO, and they develop atomic force microscopy solutions to scan silicon wafers for the semiconductor manufacturing. And our expertise is in the machine on the high-speed data acquisition and data control of the atomic force microscopy solutions. Other examples are, and it looks like my videos are not working. Another example is we are working on the development together with the Delmic, a startup company from the University of Delft, on a multi-beam electron microscope. This is really a revolution in the field. The 64 electron beams are actually scanning biological tissue, and with this electron microscope, people can scan tissue 100 times faster than with conventional single beam electron microscopes. And again, we are working on the high-speed electronics to do the data acquisition, to control the beams, etc. So there's a lot of expertise inside, but also we take care about the data storage and data management, because a lot of data comes out of this machine, and at the end, you would like to get your information out of the data. Then another example is where we ported operating systems, small operating systems, the ThreadX operating system, for a RISC-V processor, just as an example. Talking about RISC-V, Technolution is actually one of the founders of the RISC-V Foundation, which was founded in 2015-2016. Maybe you heard about RISC-V. RISC-V is an open standard. It's an open standard instruction set architecture of a processor. It is not open source. You could implement it and make the processors open source, but it's not necessarily open source. And so RISC-V offers an open standard for collaboration, where there is a default instruction set defined for the computer architecture. There's also instruction set extensions defined, and people could also implement their custom instructions. I will come to the advantages later, why we are so happy with this development and why we also use this development. And what you see nowadays is that the RISC-V community embraces a rich ecosystem with software development tools, and a lot of processor implementations. And why we chose for this RISC-V architecture is it gives us a lot of flexibility, but also portability and transparency, and I will come to that later. So we have implemented RISC-V processor IP. We call it Frenox. It's an actually a RISC-V processor family that's 100% developed at Technolution. It has no dependencies on open source implementations. It's fully implemented by us, and we also have validated it in the Intel Xilinx, I should say AMD nowadays, microsemi or microchip, and NanoExplore FPGA devices. So we actually have validated this with all kinds of FPGA devices that are around. And this computer architecture, so the RISC-V processing architecture, we use nowadays in products for secure line encryption, say in hardware VPN solution, which we as Technolution have developed, and which is also listed in the or which is NATO and EU restricted. So it could do data protection on all kinds of protection levels, from confidential up to secret and top secret protection. What is important there is that you would like to see the data encryption and the crypto algorithms implemented in hardware logic, not in software, but the control flow around you would like to implement in software, and there is where we bring in our RISC-V processors, because we have a full understanding of our custom implementation of the RISC-V processor, but we could also show transparency to the customer or the evaluator, for instance. And another advantage of using RISC-V in our case is that we could also provide lifecycle management. For instance, if there's an FPGA device, our device is obsolete, then we could choose an FPGA from a different vendor, but we could still use the same RISC-V implementation. So we could port the design easily to other vendors, and in this way show transparency to our customers. To go a step further, so we have developed the RISC-V processors for our security business line, but we also see that in Europe there is a need for European non-dependence, as they call it. So critical space technology should be developed in Europe, and we are lucky that there is a European radiation-hardened FPGA available from the French company NanoExplore. So we have also implemented our RISC-V processors in the radiation-hardened NanoExplore FPGA devices, and we have demonstrated that we could port the RISC-V processor, and they also work. So if you're interested, we have some demos available, and we could show you that. Okay, so as I mentioned, my colleagues from Technolution Prime, they are actually the technical market leaders in high assurance security applications. They have a product line with a couple of line encryption products, but also with the data diodes to separate networks, for instance. And within all those solutions, we use a combination of hardware and software, and the software is running on the RISC-V processor implementations. But now going back to space, so we do a lot of high-tech developments for the industry and also for security, defense related stuff. We could also bring this kind of technology to the space domain. And I will now give an example of a project Technolution is working on together with NLR, the Netherlands Aerospace Center. And this is a project commissioned by the Netherlands Space Office. It's a so-called SPIR project, where we will develop control and data processing electronics for instruments for small satellites. What you actually see on this slide is, on the one hand, there are the big traditional satellites. I hope you can see my mouse pointer. So at the right top, you see a traditional big satellite. On the left side, left top, we see a small CubeSat or a nano satellite. And what you see here is at the right, the traditional satellites, they are robust, takes a lot of effort, takes a lot of time, takes a lot of money to develop highly reliable, robust satellites. On the other hand, we have the CubeSats developed from commercial components, no guarantees about reliability, etc. But in between, there is a sweet spot of satellites becoming bigger compared to the CubeSats, and with satellites from in the microsat and the minisat segment becoming larger. They are becoming also a little bit more expensive, and we understand that there is a need, if you have larger satellites, that you would like to have an in-orbit lifetime of at least 5 years, so 5 to 10 years, so to say. Which is sometimes possible with CubeSats, but there is no guarantee whether those small satellites will last for a long time in orbit. So that's why we started the development together with NLR to develop control and data processing electronics that can last for more than 5 to 10 years in orbit, where we will do a trade-off of high quality and reliability, look at radiation hardened components, radiation tolerant components, or even a mix with commercial components, and provide flexibility to the instrument developer, so that he has the flexibility at design time, so that he can customize the electronics with his needs, but also in-orbit reconfiguration possibilities, and for the longer term in-orbit edge computing, like image processing in space, but also encryption in space, in order to give the instrument developer instrument autonomy, so that he could develop his instrument and just hook it onto a small set platform. So how would it look like? We know some small set use cases which are interesting. We have here a satellite that scans the Earth, and that will detect, for instance, oil leakage of a ship, or therefore it needs to do some processing in the satellite. We need to do data reduction, or you could reconfigure the satellite so that it could detect, for instance, ships with refugees on an ocean. And what is important, you would like to do this at real time, because if you detect a ship with oil leakage, you need to respond directly. We cannot just do offline processing and 1 month later say, hey, we detected the ship, because then we're too late. So latency is also important in this perspective. Other developments we see with small sats is small sat constellations. So use multiple satellites to detect anomalies from space. So, for instance, scan the Earth, and then later on instruct another satellite to zoom in into an area, like the use cases for Tropomi nowadays. But for Tropomi, with Tropomi, what's happening, we can of course monitor the emissions, but then there needs to be some offline processing, and you need to offline instruct another satellite to zoom into an area and to detect who is actually doing the gas emissions or who was a violator. With the constellation space, it will be possible that you have distributed satellites and they just cooperate as a system. But that needs also a lot of processing in space again, so adds processing in space, AI, in order to reduce latency again. Then what we will also see is that encryption becomes important for a satellite. Why? Because you would like to encrypt the instrument data, because we're living in a world of data, and data are critical, but data are also valuable. So you don't want that data is accessible to everybody. So encryption of data is needed in space. And with this upcoming constellations as a service or satellites as a service, as we have more small sats in space, we also should think about how to protect the data for multiple users, how that multiple users can use the same satellites to do their experiments. So these are issues we are looking at the moment, which will be covered by our study together with NLR to develop the control and data processing electronics. And in the end, yeah, we would like to focus on a control and data processing unit with some important onboard features. So science data encryption, but also to care about data compression and filtering. So we need a lot of processing power in space, but also at the right balance of radiation hardened or not radiation hardened. Critical components should be radiation hardened, for instance. And for the longer term, everybody is talking about AI, artificial intelligence, and that could be a means to do data processing in space. And obviously, if we go for a longer in-orbit lifetime, then also in-orbit reconfigurability becomes important. Remote access to your firmware and to your instruments, remote updates and remote diagnostics functions. So those are some keywords where we have an interest to focus on with collaborative R&D programs. In the end, the CDPU, the control and data processing unit, will have a look like this. So we have a small sat platform, and we can connect universal sensors to it. We have the bridging logic in between the sensor and the platform. This bridging logic is actually what we call the control and data processing unit, which is a modular build design, where we will have some core processing unit. There could be some optional processing units, maybe at a different quality level or different reliability level. And we will have interface modules to interface the CDPU with different sensors, depending on the needs of what kind of interfaces are needed, and also a module to connect to the spacecraft platform. And our idea is that we could reuse a lot of knowledge and know-how that we have already have from ground equipment, like the multi-beam electron microscope development, atomic force microscopy. There we have a lot of expertise with the HL electronics development, modular electronics development, and we could bring this to a level that it can also be used for space. So okay,
we're running a little bit out of time, Gerard. So if you could,
this is my last slide. So to summarize, the R&D interests for us are on data processing, controllers, secure controllers. We really see that the RISC-V processors will come up. So space technologies for European non-dependence. I could also think about smart photonics and quantum communication as possible topics.